So let's talk about what we did kind of a couple weeks ago and kind of maybe return to it a little bit and try and clear up some confusions that we had. Okay, so before, what did we look at? We looked at an example of a particle in a box, right? So we had a particle in a box, and okay, we said that our Hilbert space was what? It was all functions f um, from 0L into C, such that if I was to integrate this function from 0 to L, the absolute value squared of that function from 0 to L, I would get some finite answer, right? This was more or less the Hilbert space we're working with. And then I said, okay, on this um, space, I can write down a Hamiltonian, which is going to be p squared over 2m. Just p squared over 2m plus, yes, for now let's say p squared over 2m. This is the Hamiltonian in the within the within the box, right? Technically, this condition of placing a particle in a box and keeping it there is equivalent to saying that actually I do have a potential term that depends on space, and it's just that this potential term is equal to 0 for x in 0 to L, and is infinite for x not in 0 to L. So putting a particle in a box is kind of like trapping it with these infinite potential walls so that it costs some infinite amount of energy to leave the box, right? So, this would correspond to, something like this. Where's my colored chalk? So this is 0, this is L. Okay, very good. Um, is it anything visible from there? I don't know. Let's move the table further closer. Okay, if you guys can't see, well, you can see. Okay, and so this is a graph of the potential to, position. Okay, so this is kind of one way to think of this Hamiltonian. But because we are interested in how the wave function um, looks like inside, then inside it's just p squared over 2m, and outside we just say, well, we have to set the wave function to 0 because otherwise I need to have I cannot have some I want the wave function to be finite and integrate to something finite, and the only way to multiply something infinite by something finite and get something finite, it's 0, so that you just want to get 0. Okay, this kind of makes sense. We're trapping a particle with some infinite potential in the box. Okay, and so within the box, I just look at this Hamiltonian, and then we found the energy eigenstates of this Hamiltonian, right? Well, actually, first of all, let's remember what P is. P was minus IH bar partial x. Do you agree? Okay, so let's just rewrite this again. This is So this would be h bar squared over 2m. So there's an I squared. I get a minus sign. There's two minus signs here that cancel. So I overall get a minus sign. Minus h bar squared over 2m partial x squared. Do you agree? Yes? Okay. Now what I want to do is I want to find the energy eigenstates of my system, right? So I want to find things. I want to find something such that h of psi is equal to e of psi. Do you agree? Where e is some constant number. So this is just a simple differential equation. And we also have this added condition that whatever psi is, it has to go to 0 at 0 and L. Okay, because we're thinking that for whatever reason we can't really escape outside of this box, and I mean this is a reason that you can check in terms of just the Hamiltonian by requiring that you don't have something um, actually go to infinity. Okay, so in this case we guess that the solution has to be some constant uh, times sine and what? So it has to be pa, 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 pum. So I have that. I can rewrite this as partial x squared of psi has to equal to 2m en. Whoops. 2m en minus 2m en over h bar squared psi. Okay. So then we can guess the solution to be some constant times sine, and I can see that this has to be 2m en and all divided by h bar and times x. Okay, so this would be an eigenstate of this function. Let me see if I miswrote anything. No, everything's fine, right? But remember that before I argued that we want this to go to 0 at L, right? Does this go to 0 at 0? Yes, okay. Does this go to 0 at L? Not necessarily. So we have to force it to go to 0 at L. For this to forcefully go to 0 at L, I have the following condition. I need 2m en over h bar times L to be equal to pi times some integer n, right? Because that's where sine goes to 0. Okay, and if we were to do some basic rearrangements, which I don't want to try and do, we get the following fact. I will actually erase some bits here. We get the following. We get the following fact that the nth energy level has to be equal to h squared over 8ml squared n squared. Okay. Now h is Planck's constant. H bar is reduced Planck's constant. You may remember that I don't know. H bar is equal to h over 2 pi. Right? Is that 2 pi? That sounds right. And so that's where you get the 8 from all of a sudden, because before we had an h bar somewhere, we had an h bar here, and because we're squaring it at some point, you get 4 pi from somewhere, and then you had a 2 here, something like that. Okay, good. So that's why this is review. Don't worry, there will be some new things. Okay. Now, but we also had, these other two operators. So, H bar was one of them. Sorry, not H bar. The Hamiltonian was one observable that we had before. Do you agree? We also had two other observables that we noticed that we may have. And what were these two other observables? Do you remember? P and X, yes. So you had P, which was equal to minus IH bar partial X. And you had X, which was just, multiplication by X. Do you agree? And we had that their commutator was X and P, which is just multiplication by IH bar. Do people remember what the commutator is? Yes? Okay. And so last time, what did we show um, for what fact did we show about X and P? And for the people who did the suggested exercises, what did you show in the suggested exercises? Yes, so the product of the uncertainties of X and P is greater than um, H bar over 2, right? So this is something that we showed. This is something that we showed last time. Remember, this involved like Cauchy's inequality and the fact that the norm of a complex number is always greater than one of its, like its imaginary part or something, right? This is what this calculation involved. And so this uncertainty, the standard deviation, you can kind of think of, as the kind of spread for what you can get for as an outcome of your measurement. You have some possible outcomes you can have in your state. What is the possible spread of these things? Okay. So now there's one thing that we tried when we first did this particle in a box example that didn't really work out. What was it? When we did particle in a box, like a few weeks ago, like still during the year, we tried to do one thing first, and then it wasn't working out. And I was like, okay, we'll think about this later. And then we computed the energy eigenstates instead. What was the thing that didn't really work out? It is somehow related to the orange part of the board. We tried to compute the eigenstates of something else. What was it? Yes, we tried to compute the eigenstates of momentum. And when we computed the eigenstates of momentum, right, we got what? So um, we wanted for an eigenstate of momentum, we wanted P of psi to be equal to some K psi, where K would be our momentum, right? And when we were doing that, okay, well, you can just, this is very easy, right? This is minus IH bar partial x of psi has to equal to K psi, right? I bring this over to the other side, so I get that psi has to be equal to E to the IK over H bar x. Do you agree? Is there an H bar? Yeah, sure. Okay, but then what was the difficulty with this guy? Why is this person so problematic? Well, k to be a real number, yes, sure. Suppose k is a real number. Well, sure. K is real. Suppose k is real. We have bigger problems. What is our Hilbert space? Actually, yeah, I forgot. I forgot to add to our Hilbert space that f of 0 equals f of L equals 0. Okay. What is the problem? Yes, this guy cannot be 0 at 0. Well, at 0, definitely not 0. And at L, um, also can't make the 0. Why can you not make the 0? Because as you may remember, e to the I theta anything, right, has to be equal to cos theta plus I sine theta, right? If you take the absolute value of these two bits, that's equal to cos squared plus sine squared equal to 1. So this always has norm 1 anywhere as a imaginary number, right? So this cannot fit these box boundary conditions, right? It just doesn't work. Now, why does this make perfect sense in terms of the uncertainty principle? So suppose our state, we were in a momentum eigenstate, right? Suppose we were in a momentum eigenstate. And we did a measurement of, like we started doing, momentum measurements on it, right? So what is the expectation value of this measurement? It would just be the whatever momentum that the state is in. Okay, what would be the uncertainty of that measurement? 0, because there's only one. If we're in an eigenstate of momentum, right, that means there's only one possible outcome, right, which is the momentum, the eigenstate of momentum in which we're already in, right? So this means that the uncertainty in position is 0. Okay, what does that mean about the uncertainty in x? Yes, the uncertainty in x has to be somehow infinite. Okay, when I say the uncertainty is infinite, this is like not rigorous. This is like hand wavy. But okay, you understand what this means. What does this mean? This means that all of a sudden, our particle should have probability to be anywhere, not just in the box, but literally anywhere, because infinity is a lot larger than L. Yes, we agree. So this means that if we had momentum eigenstates for the particle in a box, that means that that eigenstate has to have somehow some infinite spread. Do you agree? Which well, you can't have because we demanded the particle stay in the box, right? With an infinite potential. So kind of from the uncertainty principle, we see why we now see why we were having so much difficulty getting this thing to kind of work nicely with the boundary conditions, because if we had a momentum eigenstate, we would have something that is somehow infinitely spread in space, which we can't have. And I mean, this is exactly what we're getting, right? If you look at this wave function, this wave function has some kind of infinite spread, everywhere. And okay, yeah, so you can't put it in a box. You can't give it 0 boundary conditions on the edges, okay? Does this part make sense? Um, so I strongly suggest people do the suggested exercises from last week and the suggested exercises I will give this week. The suggested exercises from last week are like directly relevant to helping you understand, whatever particle in a box stuff you're doing in 256. And the suggested exercises from this week will be relevant to a little bit of that and other things. Okay. Very good. So, okay, we kind of have some sense of, right, sorry. And so I should have kind of stated that, in general, sigma x should be somehow constrained. It should be somehow less than L, intuitively at least, right? Because I shouldn't have the ability to be anywhere outside of my box, right? So there shouldn't be any measurements that I can make outside of the box. So I shouldn't be, more than L away from, any point, any possible measurement. Okay? Right. Okay. Do you agree? Yes, no? Questions? Okay. So, mm, okay. So now, okay, we've kind of dealt with position eigenstates in the sense that we realized we won't have momentum eigenstates. Sorry. Kind of dealt with momentum eigenstates by realizing in our system we can't have momentum eigenstates. Okay? But I mean, position eigenstates are probably fair game, right? I can be in my box, I can be in a particular, in a particular place. Degree in the box, right? Pardon? Yeah, exactly. I can be in a particular place in my box. And okay, if I'm in a particular place in my box, then that means the spread of momentum can be anything, right? So the particle can have any momentum within the box. But I mean, that's fine because we don't really have any condition on, sigma p being less than anything. We only have a condition on sigma x being less than something. Okay? So in principle, we should be able to figure out what the um, position eigenstates of what the eigenstates of the position operator are. Yes. Okay. So let's write down some eigenvalue equation for this. So we want x psi is equal to lambda psi. Do you agree? Okay. Um, well, this is also kind of problematic, right? Does anyone have any suggestions for solutions to this? Zero is not a solution to this. Well, I guess zero is a solution to this. You're right. But we want our wave functions to somehow be, normalized to one as well, right? We want that to be finite, and actually you want it to still be greater than zero. You don't want the zero function because that's just, oh, I have no particle in a box. Well, that doesn't describe my system because I said it's a particle in a box system, so there's at least, something. Okay, so this is not okay. This is not obvious how to solve this. What would solve this, right? Because you need at least, something. You want this to be non-zero at least somewhere, and if it's non-zero there, well, you know, clearly as x changes, lambda would have to change. So this wouldn't work, right? Right? X is not equal to lambda everywhere if lambda is a constant. So how are we going to proceed with this? We're going to start and kind of try and do something intuitive, and then we won't necessarily make it rigorous. I will just kind of tell you that, okay, it is possible to make this more rigorous, but we won't really do it because it would take too much time. You guys have to leave at 12, right? Oh, class. Oh, yeah. Okay. Well, then if you leave at 12:30, okay. Well, you're gonna have to use the city bikes. Okay. Okay, I'll try and finish in about an hour. Okay, so what are we going to do? We want it so that multiplication by x is essentially like multiplying by a constant. Do you agree? And we also our wave function want our wave function to be normalized. So we want the integral of the thing squared, the absolute value of the thing squared, to be equal to 1. Do you agree? That's what we want. Okay, so let's draw a picture. Okay, I want some wave function such that if I multiply it by x, I'm multiplying it by a constant. Okay, we know that we can't do this. There doesn't exist a function that does this. So let's try something that kind of does this, right? Okay, suppose I have my, so it's going to be L. Suppose I have my, maybe I want to use this color for L. Suppose I want an eigenvalue lambda here. Do you agree? In principle, what I could think of doing is I could draw a function that is 0 everywhere. Then here it has some kind of thin peak, and then is 0 outside of this. Okay, do you agree? And suppose this peak has width 1 over epsilon. Yes, 1 over epsilon. Where epsilon is some small number that we will specify later. Okay, if I want this to be 1 over epsilon, to make this integral to be 1, what do I need the height of the function to be? Yes, because 1 over epsilon times epsilon is 1. Okay, thank you. Ever since taking summer courses, you guys have become so much more sad and depressed. Yes. Okay, maybe we should have the reading group twice a week. Okay, so we can think of this kind of indicator function. Do you agree? This kind of indicator function, let's call it, I don't know. We can call this, so usually when you have an indicator function, you have this thing called chi, and then maybe you put some set a. This is usually defined to be a function which is 1 for x and a and 0 else. Right? In this case, I guess our function is chi lambda minus 1 over epsilon, lambda plus 1 over epsilon, and so this is epsilon times chi. This is our function. Okay, this is just silly notation. You agree? Okay, does this solve our problem? No, but this is pretty good, because if I take epsilon sufficiently large, right, then so my integral is exactly 1, right? And x is not going to change too much over this little thing of 1 over epsilon, so it's almost like I'm multiplying by a constant, right? Do you agree? Maybe? Yes? Okay, so then the kind of mathematical question you might say, okay, well, okay, I could take epsilon and I can actually define some epsilon n, right, equal to, say, n. Do you agree? So what do I get? I get a sequence of these indicator functions. Do you agree? I get a sequence of these functions. Let's honestly call them fn. So fn is equal to n times this thing lambda minus 1 over n lambda plus 1 over n. Okay. So I can take this sequence of functions, and okay, functions are, these are all vectors in our vector space, in our Hilbert space here. I have an inner product on this Hilbert space. Do people remember what the inner product was? What was the inner product? I should have said this earlier at the beginning. I forgot. Sorry. not just the product. There was something else. So was equal to. Yes, it would be. Well, we're gonna want it to be. We're using physicist notation, so we're going to want um, this thing to be the conjugate. So phi dx from 0 to L. Okay, so this was the inner product. This is very important. Okay. Well, one question I can ask is, okay, we have that inner product, right? So we have a norm from that inner product. Do you agree? So we can ask, is this a Cauchy sequence in the norm? So is this Cauchy? What do people think? Is this a Cauchy sequence where, kind of take these taller and taller peaks that are thinner and thinner? Is this a Cauchy sequence? Yeah, last time I checked yesterday, and I don't think it is either. So it is not a Cauchy sequence. It does not converge in this space. But okay, what do we mean by converge? So it does not converge using the norm. So not Cauchy in the sense that does not converge strongly. Meaning that not converge. So meaning that the norm of phi n over phi m, is not less than epsilon for n m greater than some n, right? So this is what we mean by does not converge strongly. They don't get closer to each other in the norm induced by the inner product. But you could define a thing called weak convergence. And this is something people do define. And so, okay, this is going to be one of the suggested exercises. Show that these kind of things don't converge strongly. It's a very easy analysis statement. Well, because the functions are very easy. So weak convergence. Weak convergence goes as follows. We say that Fn converges to F if the inner product between Fn and phi converges to F with phi for any phi in our Hilbert space. Hilbert space, or really Euclidean space, any space with a norm. So this is another kind of convergence I can define. So this weak convergence, it's not as good as strong convergence, but at least I have that my inner products between states converge. Do you agree? Okay. Okay, and you can check, well, that actually we can write down something that will, that this will, we want to write down something, some f, such that, you know, this inner product somehow converges to this, right? I want to write down something such that this converges to this. Okay. Now we're going to recall a fact from 247, which I'm not going to discuss in too great detail, is that we have the Riesz representation theorem. Do you remember? Yes? Riesz representation theorem? So the Riesz representation theorem, I don't know. it doesn't matter. But the point is that if I have f in my vector space, right? Well, if my vector space has some inner product on it, if f is in the vector space, then there's a natural mapping from, there's a natural mapping from V to V dual. In what way? I take f and I send it to, a functional like this. Or maybe I want it in the second slot or something. Yes, maybe. So I may have accidentally swapped. Here I'm using mathematician's notation where the thing is linear in the first entry. So now I'm swapping back. Now our inner product is linear in the first entry. So yes. So do you agree? If I plug, oh no, sorry, lies. Yeah, it's still linear in the second entry, right? Sorry. So do you see how mapping this to this is a linear function, right? Because I can plug in something into the second entry. It's linear in the second entry, so this is a linear function, right? So I can think of f as, a linear functional. Right? There's at least a mapping, from V to V dual. There's not always a mapping back from V dual to V, but the Riesz representation theorem says that for finite dimensional vector spaces, there is a mapping back, right? And then for, separable Hilbert spaces, there is also a mapping back. Okay, but we aren't necessarily restricting ourselves to separable Hilbert spaces. Okay, do you agree? Yes. So you agree that such a map, this is indeed a linear map from V to V star. Yes. Okay. So perhaps I have these Fn, these Fn would converge to some F, such that um, something like this, that this number converges to this number for all phi in the Hilbert space. And so far, we've been trying to find an f like this in the Hilbert space itself, right? In this vector space. Do you agree? But we now realize that, hey, I could be thinking of this as, some linear functional converging to some other linear functional kind of value by value. Because that's what this is saying, right? If I fix Fn, right, this is like applying Fn, applying this dual of Fn to phi. Do you agree? This is like applying some functional to f, to phi as well. Do you agree? So this is kind of, I'm trying to, perhaps I shouldn't be searching for, this in the vector space. Perhaps I should be searching for f in the dual space. So key idea. So perhaps need to search for eigenstate of x in the dual space. Do you agree? Yes, maybe. And in fact, okay, I'm going to erase all of this. Hopefully this makes sense. Okay, so let's figure out what functional we're trying to, what functional this is going to, these kind of bumps are going to weakly converge to. Okay, so now I've rephrased the problem. Now instead of searching for a function, I'm going to search for a linear functional that this converges to. Okay, do you agree? Does that make sense? So people remember what a linear function is, right? I take in a vector, I output a number. Oh, okay, yeah, that's all I'm saying. Yes, the dual space is the space of functionals. Yes. Okay. If you don't, if I'm saying a word and you don't know what the word is, like it's fine. You should just ask. Because we didn't really talk about functionals in any of our meetings. I was just like, oh, you talked about this. Like, I don't know. I told you this in tutorial, surely. Okay. So that's very good. So we're trying to see if I have these bump functions. So this is so I'm just gonna rewrite this statement of weak convergence just in terms of the actual inner product, and like use these specific bump functions that I came up with, right? I'm trying to use these bump functions to somehow approximate an eigenstate of x. And so let's write down the exact integration conditions for this. So this is from 0 to L chi n minus 1 over, lambda minus 1 over n, comma, lambda plus 1 over n, multiplied by, any function. And maybe I want what? I want this to be barred. Okay. Dx. Do you agree? Okay, now this chi function is, so it's 0 outside of this set and 1 on this set. So how can I rewrite this integral to get rid of this chi function? Yes. So lambda minus 1 over n, lambda plus 1 over n dx. Do you agree? True. Well, true. 2 yeah, I wrote this wrong earlier. 2 okay. 2 okay. X to be normalized? We don't need X to be normalized. We want the eigenstate of X to be normalized. Why? Because I'm saying Fn is something that looks kind of like an eigenstate of X. It's not an eigenstate. Fn is not an eigenstate of X. But it's like, it's kind of like one. Do you agree? Because it's just a tall bump, right? The area under the bump is 1. Do you agree? If I multiply this by x, I integrate it. If the bump is very thin, x does not change too much. So it's almost like I'm multiplying by a single number. Almost. Do you see do you understand why we're looking at these bumps to begin with? Kind of? Yes? Okay. And so I'm trying to find something that these bumps should converge to, right? At least in a weak sense. And we realize that, okay, this is not going to converge to anything in the strong sense in our Hilbert space. So perhaps we realize that we can think of these bumps instead as elements in the dual space. And so we should see if this converges to anything in the dual space. Do you agree? Yes? No? Maybe? Okay. So we're trying to see if this converges to anything in the dual space. Okay, and so we're trying to see what this, converges to in the dual space. Okay. Let's try and figure out what this integral should be as n kind of goes to infinity. Okay? So, oh, okay, that hurt. So I can kind of, yes. So what do people think this is going to converge to as I increase n? What would this integral converge to as I increase n arbitrarily? Thoughts? Yes. So intuitively it should be 5 lambda. Or sorry, 5 lambda. My bad, sorry. I lied again. There is no bar here. There is a bar here, but since this is real, there is no bar. I'm very sorry. I messed up my conventions again. The inner product is linear in the second entry. And so there should be a bar here, but these are real numbers. I'm very sorry. I'm confusing you over and over again. So this should be, that's true. So this should converge to 5 lambda. Okay. Does it converge to 5 lambda as I increase n? Does this integral converge to 5 lambda? It's a 50-50. There's 3 of you. One of you will get it right. Yes, it does. Let's check this very easily. How are we going to check that this does indeed converge? Well, I'm going to do what? I'm going to take lambda plus 1 over 2n, lambda minus 1 over 2n, and phi of x dx. Then I'm going to subtract phi of lambda. And I'm just going to show that, this as a number, can be made less than any, I don't know, epsilon, delta, whatever you want. Okay? How can we do this? Okay, let's assume that phi is a very nice function, so it's like somehow, continuous at least. So assume phi is continuous. Do you agree? Then for any given phi, I can find find a n, right? Such that phi of x minus phi of lambda is less than, I don't know, some epsilon on this interval. Do you agree? If phi is nice and continuous, this is just a statement of continuity that I can find such an n. Yes? People remember this from analysis? Okay, good. So this means I can replace this integral and say, okay, this part, so has to be, so this part has to be less than, has to be less than this integral, lambda minus 1 over 2n, lambda plus 1 over 2n. So if I was to subtract, what am I saying? Yes, so this integral n times, phi of lambda maybe plus epsilon. Do you agree? Dx. Okay, this is a constant of some sort. So maybe phi of lambda. Well, sorry. This is less than phi of lambda plus minus epsilon. So sorry. This has to be. Why am I trolling? So the absolute value of this has to be less than. I can replace phi of x with. Okay, I would need to subtract this, but okay. The point that I can say is that this is approximately phi of lambda up to some. I'm not going to do the full proof. Up to some vanishingly small term that I can control somehow. Okay, dx, and so I still have minus phi of lambda. Do you agree? And then, so I'm being hand wavy again, but okay, I can make this rigorous. I just don't want to spend time because I'm making a mistake. Okay, but then this is now just some constant that I'm integrating over something of width 1 over n. Do you agree? If I multiply this by, 1 over n, which is what this integral is, this is just going to be phi of lambda plus epsilon minus phi of lambda, right? Which is, epsilon. So, and since I could, choose what this epsilon is, I can make this kind of arbitrary small. arbitrarily small. Sorry, this step is poorly written. There's a better way to rewrite this step. Okay, but the point is that integrating these bump functions with any other function, if I increase n, that converges to just the value. This integral just converges to the value of that function. That's what is important. Do you agree? Value of that function at lambda. Okay. And so what did we get? What did we get? We got a linear functional. So this converged to some linear functional. What is this linear functional that this converged to? It's a linear functional that takes a function and tells you what? The value of the function at lambda. Do you agree? Okay, I mean, that's a valid linear functional. I just, you give me a function, I tell you the value of that function at a specific point, right? That's a valid linear functional. So this is like the evaluation. So this converges to, Fn, let's write this like this. Fn converges to the evaluate at lambda functional. So what does it do? It takes a number, it takes a function and sends it to phi of lambda. Okay? Do you agree that this is indeed a linear functional on the space of functions? Right? If I give you the sum of two functions, right, and I evaluate those at lambda, that's just going to be the sum of the values at lambda. Right? Just by definition. So this is indeed a linear functional. This is indeed in the dual space of my Hilbert space. Everything's very good. Do you agree? So, okay. So we found that this converges to some functional. But clearly we saw that this functional doesn't have anything mapped to it from the vector space. Okay? But we want to still write down some kind of notation to make it look like, something, something. So, I'm going to define the following object. So I'll actually erase this part because I don't want you to look at this because this is poorly done. This is not entirely correct. So don't look at this. I will erase this. So we will now define the delta function, which is not a function. So the delta function is a linear functional. It's not a function. It's a linear functional, which evaluates, which acts on, functions. So is a linear functional on kind of on some space of functions. Which acts on functions by evaluating them at some point. Okay? Now, we wanted to write this down we wanted to write this down as something that we can put into an integral here, right? We wanted to write down this converges to, so this converges to some kind of thing that if I, multiply it by phi dx, I get phi of lambda. Do you agree? We wanted to write it down in this form based on this kind of thing that we wanted this to weakly converge somehow. Do you agree? This is just me rewriting this. Okay? So I will then write it as, so the delta function of x minus lambda. And is going to have the defining property that, so such that x minus lambda integrated with phi of x dx, so this is from a to b, is equal to phi of phi of lambda if lambda is in a to b and 0 otherwise. So this is kind of abusive notation in some sense, right? Because I want to write down something such that if I integrate it, I get this evaluation functional. And so instead, maybe I can think of this, maybe I can attempt to think of this linear functional as still some really weird function. It's not a function. And so one thing that we kind of have to realize directly from this is, okay, so first of all, what is the norm of, actually, maybe, yes, maybe let's not ask that question yet. So, okay, one thing that you should realize immediately from this is that if I was to just to integrate the delta function without anything, I just get 1, right? If lambda is in AB, right? Because this is, like I said, phi to be equal to 1, right? Do you see how this follows from that statement? Okay. Good. And one way that physicists often try and explain this delta function thing is that the delta function is, delta of x is somehow infinite at x equals 0 and 0 everywhere else, and that and it has this property. And this is how physicists often try and explain this, that it's some just very immediately sharp peak at 0, and then it's 0 everywhere else. And so that's kind of how physicists explain that it's something that gives it this property. Okay, and that its integral is 1. Oh well, its integral is 1. Okay. Okay. So what is the delta function in a math sense? Yes, it's a linear functional. And we just find a notation that writes down this linear functional as if it was a function. Okay? Does this kind of make sense? No. We want to write down a linear functional as we want to find a function f such that it maps, so we have some linear functional, let's call it delta, and we want to find something f that maps to this linear functional where, this is equal to our delta function, but then nothing like this exists. So I just kind of, make up notation for what this, should be, as if it did exist. And this is not visible in here. Okay. So let's see. Did this solve our problem of finding an eigenstate for the position operator? Pardon? No, it did. Yes. Because now if I take this delta function, I multiply it by x. Do you agree? And then and I multiply it by x, right? If we use kind of this logic, right? Um, this delta function is 0 everywhere except for at one point. And so then multiplying it by x is exactly multiplying it by, the um, value of x at that one point where it's not 0. So in fact, the delta function is an eigenstate of my position operator, but it's an eigenstate in the sense that here we're thinking of x as acting on the space of linear functionals, which, I mean, it can, right? X also acts on the space of linear functionals because I can, multiply something by I can, if I have this identification that some function whoops that's that some function gets mapped to a linear functional like this. If I can multiply the function by x, I can multiply the functional by x by multiplying by x in here. Okay, so we'll now make this miraculous claim that we were searching for an eigenfunction of x in the Hilbert space. We didn't find one in the Hilbert space, but we found something that looks like it in the space of in the dual space. So we found eigenstate of x in the dual space. In the dual space. Okay. So perhaps the Hilbert space that we should be working with, maybe it shouldn't necessarily be the original Hilbert space, maybe it should be the dual space. Okay, but that's a much more technical point, and there's a lot more to say about this, and I don't want to say it. Because then I'd need to be very precise, and I have not prepared to be very precise. Okay. Do you agree? Now, now we're going to compute some things. Okay. So the defining properties of the delta function that are really important are really just this. Is this property with the integral? Oh, whoops. This property. Okay. We might be getting kicked out. I don't know. Okay. So that's very good. Now let's try and compute something with this. So I'm going to claim that the eigenstates, so we found eigenstate of x in the dual space, and instead of writing down in the dual space, we abuse notation and pretend as if it's something coming from the function space, even though it's not. So we write, so delta x minus lambda as a function that maps to this desired functional via Okay, so now I've kind of manually added this kind of weird thing into my Hilbert space. I've kind of manually added this thing. And okay, yes, I've manually added this thing. It can't really be part of this Hilbert space, but we can just, manually add a thing and hope that we get the physically correct things that we would like. And so now let's try and compute something, right? One thing that we would like to compute is, for example, suppose I have my wave function, right? Suppose I have some wave function psi, and I want to write it in terms of the basis, in terms of the basis of these, eigenstates, these delta function eigenstates, right? This means that what? Okay. What should these delta function eigenstates be? Right. So ideally, I'd write phi like intuitively. So intuitively, this is not rigorous. I would somehow want to write phi as sum of some positions of x, sum ax times delta functions x minus x prime. Do you agree? This is something that I would like to write. I would like to rewrite psi in terms of this delta function basis somehow, right? By this analogy, you may recall that these ax's should be just the integral of the delta function against psi. Do you agree? Okay. But what is this integral equal to? Psi, yes, exactly. Okay. So we can, we can compute these coefficients. That's good. And maybe what we're realizing, this is somehow continuous, right? Because x is somehow a continuous variable. So maybe this sum should be not a sum, but instead a integral. Okay, so really I just wrote this down here, right? Somehow psi should be some, yes, so let's plug this back into here. So this sum should be an integral because x prime is somehow a continuous variable. Do you agree? And let's check if this makes sense. So in this case, I would expect psi of x to be equal to the integral by dx prime. Yes, hello? Do you have this room booked?
You have this room booked?
I had it booked from 10 to 11.
Yeah,
we're going a bit
I think
over.
it's 11. Yeah, we have our journal club.
Oh,
so...
I'm sorry. You guys should have told me.
No, we're running a bit late today.
So oh,
okay. Are you?
Maybe 7 minutes?
That's okay.
Okay, thanks. Okay, so we have to finish this point. Okay, so let's just, so it's a sum of dx prime, and I want to be doing ax prime times delta xx x minus prime. So I know what ax prime is. Ax prime is this integral of delta x minus x prime psi of x dx. And then I also want to multiply this by a delta function of, so let's do a twiddle, not to get confused by all the x's. Okay, I got that this integral, we saw that this has to be phi of x prime. So I get psi x prime delta minus x prime. Do you agree? And well, this just gives me, okay, this just gives me this back. Okay. So I see that this kind of intuitive idea that I can rewrite psi as some sum of delta functions kind of makes sense. Vaguely. Kind of makes sense. Do you agree? A little bit? Yes? Maybe? Okay. But here kind of the difference is that this is not really a sum, this is an integral. Why? Because if this was really a sum and you were trying to compute the probability of being at a specific point, right? The probability of being exactly at x should always be 0, right? So this has to be an integral because then you would be integrating something over like a single point. And if you're integrating something over a single point, that would be somehow measure 0, so you should somehow get 0. Okay. And so I'm going to now make the last claim, which you will have hopefully seen with in 256 already, but this will be kind of, we semi-rigorously, well, barely rigorously, but I said some math words in there, so I guess I can claim that we did something. Argued why this has to be the case, purely in terms of trying to find eigenstates of x. Okay, so I want to compute the probability. So probability of measuring particle to be in this region AB. Do you agree? Okay. So intuitively, what should I be doing? I should sum up, take a sum over all x in AB, the probabilities of me being at x. Do you agree? But this sum we will turn into an integral instead, because I'm doing some continuous thing, so I should replace this with the integral. So this is intuitively. Okay. Now, what should the probability of being exactly at x be? The probability of being exactly at x should be, well, it should be the absolute value of the position of x prime minus x, right? The probability has to be this because this is kind of by the postulates of quantum mechanics. You're taking the eigenstate with that eigenvalue, you're taking an inner product with the function, you're taking the absolute value squared, right? This is just like a postulate of quantum mechanics. Do you agree? Yes? Yes, okay. And so in that case, well, in that case, so then the probability to be in AB has to be, I'm going to replace this sum with an integral over AB, from A to B, over dx. And then I need to integrate this probability squared. Okay. But, okay, what is this probability? What is this inner product? This inner product is what? It's the integral from where to where? From, in our case, from 0 to L, right? Because we're, supposedly still in a box. From 0 to L of the delta function x prime minus x, phi of x prime dx prime squared. Do you agree? But what is this integral evaluate to? Yes, you can. Just look at it. It's stated. It is stated. It is stated. Please read off the answer. This integral. I have a delta function shifted to x, multiplied by something. I take the integral. Just this part. 5x. Yes. This goes to 5x based just by reading this. Yes? Do we agree? Do you see how this being 5x follows from that? Okay. So then this is just the integral from a to b dx of phi of x squared. Okay. Have you seen this before in your quantum mechanics course? So the probability of detecting a particle in some region AB is just the the integral of the wave function squared. You've not seen that still in quantum mechanics? Okay, that's fine. And so in that case, the one thing that you can really say is that now we have an interpretation of what these wave functions mean. So you can now think, we've now shown, think that these psi of x are probability densities for position of particle. So suppose I had some wave function, whatever it is, right? And I wanted to compute what is the probability that the particle is in this region. Then all I would need to do is take this function, square it. So, square it. And then, so suppose this is already the graph of phi squared. Square the absolute value of this and compute the area under this curve. And the area under this curve would tell you the probability that the particle is in that region. Okay? And this is where I will end it now, because people have this room booked.